Okay, now let's look at to the next example. Okay, previously in the example 3, we solve our x, okay, by when we have a perfect square. So we just square root both sides. Okay, as for this, okay, to solve this problem, okay, it's either we make assumption or simplifying the equation, or we have to solve by using quadratic equation. Okay, so let's look at to the question first. Okay, this is a reaction of the COCl2 produce CO plus Cl2. The Kc is given as 8.3 times 10 power of negative 4. So the question asks us to calculate the concentration of the components of the reaction COCl2 and COCl2 when the following amount of the phosgene is decomposed and reach equilibrium. Okay, means that we have to calculate their concentration at the equilibrium. So as usual, identify the information that we have. We have Kc, and then we have the volume of the container is 10 liter, and the starting amount, it's either 5 mole or 0.1 mole of the COCl2. So to solve this problem, okay, we start with calculating the concentration of the COCl2 in both question A and B. So the concentration of the COCl2 when 5 mole is introduced is 5 mole divided with the volume 10 liter, then we'll get the concentration is equal to 0.5 molar. That is for A. When the initial amount is 0.1 mole, then we calculate the concentration is 0.1 mole divided with 10 liter flask, then we'll get the concentration is 0.01 molar. Okay. Now, remember before this, when it is 5 mole, it is 0.5 molar. Okay. So to solve this, we have to construct our ice table. COCl2 tends to CO2 plus Cl2. Concentration initial is 0.5 molar. 0 concentration change is minus x plus x plus x. Concentration at the equilibrium 0.5 minus x, x and x. So when we write the Kc expression, Kc is equal to the concentration of the CO2 power of 1, Cl2 power of 1 over concentration of the COCl2 power of 1, which is equal to x squared over 0.5 minus x. So this is not the perfect square. So to solve this problem, okay, as I said just now, we can make assumption or we can solve it by using quadratic equation. Let's try to make assumption. In not all question we can solve it by making assumption. Okay, our assumption is, since that the Kc that is given is considered as a small Kc, which is 10 power of negative 4, we can assume that 0.5 minus x is actually almost equal to 0.5 because of the Kc that is too small. Okay, when Kc is too small, we can assume that 0.5 minus x is almost equal to 0.5. Okay, however, we have to check this assumption before we can use it. Okay, so the way to identify it, the way to decide, okay, whether we can assume that 0.5 minus x is almost equal to 0.5 or not, is by looking, if you look at your textbook, it is in the page of 768. Okay, if the initial concentration over Kc is greater than 400, then we can we can use the assumption, we can simplify our equation. And however, if the initial concentration over Kc is less than 400, then we cannot make that assumption. Okay, we cannot neglect the value of x. Okay, so please remember this. Now, by using this formula, we have to identify whether x can be neglected. So initial amount of the COCl2 over Kc is equal to 0.5 over 8.3 times 10 negative 4. So it is equal to 602. Okay, which is bigger than 400. So x can be neglected. And x can be neglected. So come back with the Kc expression. Now 8.3 times 10 power of negative 4 is equal to x squared over 0.5 minus x. So we have to write this 0. Since that, we have to write, since Kc is small, so 0.5 minus x is almost equal to 0.5. Okay, so we have to make a table for this. So it will be equal to x over 0.5. Then we solve our x, so x is almost equal to 2 times 10 power of negative 2. So we can get the concentration of the CO2, which is equal to the concentration of the Cl2, is equal to 2 times 10 negative 2 molar. As for the concentration of the COCl2, it is 0.5 minus 2 times 10 negative 2, so it is equal to 4.8 times 10 negative 2 molar. Problem solved. So this is how we answer this question, okay, by making assumption. Okay, let's look at part B. Okay, with the starting amount of the COCl2 is 0.1 mole. Just now we have calculated the concentration of this in 10 liter flask is equal to 0.01 molar. So construct our ice table. COCl2 produced CO plus Cl2, initial concentration of the COCl2 is 0.1 molar. Okay, sorry, 0.01 molar, 0 for CO, 0 for Cl2. Concentration change here is negative x plus x plus x. So at the equilibrium, this equal to 0.01 minus x, x and x. So when we write the Kc expression, it is equal to CO power of 1, Cl2 power of 1, COCl2 concentration power of 1, which is equal to x squared over 0.01 minus x. So now we have to decide whether this 0.01 minus x can be just simplified to 0.01. Can we neglect the x value? By using the same method as before, we have to calculate the initial concentration, divide with the Kc value. So the initial concentration of the COCl2 divide with the Kc is equal to 0.01 over 8.3 times 10 negative 4 is equal to 12. Equal to 12 means that it is less than 400. So we cannot make assumption and we cannot neglect our x value. Means that to solve our x, we have to use quadratic equation. Okay, so continue with the Kc expression. So Kc is equal to 8.3 times 10 power of negative 4 is equal to x squared over 0.01 minus x. And then expand the equation, we'll get x squared plus 8.3 times 10 negative 4 x minus 8 negative 6 is equal to, it is equal to 0. And then just press the calculator, then we'll get our x value is equal to 2.5 times 10 negative 3. So when x is 2.5 times 10 power of negative 3, then we know that the concentration of the CO is equal to the concentration of the Cl2 is equal to 2.5 times 10 negative 3 molar. And for the concentration of the COCl2, it is equal to 0.01 minus 2.5 times 10 negative 3. It is equal to 7.5 times 10 power of negative 3 molar. So problem solved. Okay, so this is the answer. So the last example that I want to discuss with you is when all components was introduced in a reaction container. Okay, so when we look at to this question, we have a reaction of the CH4 plus 2H2S produce CS2 and 4H2. Okay, so in the experiment, 1 mole of the CH4 was introduced, 1 mole of the CS2 introduced, 2 mole of the H2S, and 2 mole of the H2 mixed in 250 ml vessel at 960 degrees C. Okay, so let's highlight all the important information that we have. 1 mole CH4, 1 mole CS2, 2 mole H2S, and 2 mole of the H2 that is mixed in 250 ml of reaction vessel. Kc is given as 0.036. So the first question, in which direction the reaction proceed? Okay, which direction the reaction proceed to reach the equilibrium? Okay, automatically we know that to answer this question we have to calculate the QC value and compare it with our KC. So let's solve this first. So to solve this, we have to convert all the amount that is given from mole to concentration. So I have calculated for you here. Okay, so for the CH4, 1 mole over 0.25 liter, the concentration is 4 molar. H2S, 2 mole over 0.25 liter, the concentration is 8 molar. As for the CS2, 1 mole over 0.25 liter, the concentration is 4 molar. And for the H2, 2 mole over 0.25 liter, the concentration is 8 molar. So we will just use this value to calculate our QC. QC is equal to, always start with the expression CS2 multiply with the H2 power of 4 over the concentration of CH4 multiply with the concentration of the H2S power of 2. Plug in the value, so we'll get 4 multiply with 8 power of 2 over 4 multiply with 8, sorry, this is power of 4, this is power of 2. Then we'll get our QC is equal to 64. So when we compare our QC is 64 with the KC 0.036, then we know that okay, QC is greater than KC. So reaction proceed or progressing to the left. When the QC value is greater than KC, it means that at this moment our product, which is CS2 and H2, become a reactant and it is producing CH4 and H2S. So CH4 and H2S become product at this moment. Now solve question A, look at to B. If the initial concentration of the CH4 is 5.56 molar, what is the equilibrium concentration of other substance? Okay, so we have the initial we have the equilibrium concentration of CH4 only. Then we have to calculate the concentration of other component at the equilibrium. Okay, so as usual, to solve this, we have to construct our ice table in B. Construct the ice table. So it is CH4 react with 2H2S, produce CS2 plus 4H2. concentration initial, 4 molar, 8 molar, 4 molar, 8 molar. This is what we have calculated before. So the concentration change here will be plus x plus 2x minus x minus 4x. Okay, so normally, okay, our reactant side amount change or the concentration change will be negative, while the product side will be positive. However, as for this question, we have calculated our QC first, and we know that the reaction is progressing to the left. So when the reaction is progressing to the left, that is why the amount of the CS2 and H2 decrease with time, and we put it as negative x and negative 4x. If let's say when you calculate, if you get other question, when you get the QC value and it is less than KC value, means that at that time the reaction is progressing to the right. So during that time, okay, the reactant side will be negative as usual, and the product side positive as usual. Okay, so let's continue. So the concentration at the equilibrium is equal to 4 plus x, 8 plus x, 4 minus x, 8 minus 4x. Okay, and then we know that we have to solve the x to get the concentration at the equilibrium, but the information that we get in the question is the concentration of CH4 at the equilibrium is 5.56. So CH4 concentration at the equilibrium is 4 plus x is equal to 5.56. So we solve our x, it is equal to 1.56. Now we can solve the concentration of the H2S. At the equilibrium is 8 plus x, which is equal to 9.56 molar. It will be 11.12 molar, and then the concentration of the CS2 at the equilibrium is equal to 4 minus x, so that it is equal to 2.44 molar. And lastly, the concentration of the H2 is equal to 8 minus 4x and equal to 1.76 molar. Okay, so this is the answer that we are looking for. With all these 5 examples, okay, I hope that it can help you when you get a question regarding the equilibrium problem. Okay, there will be more varieties question that you will find later. Okay, so good luck.